Well, let's go ahead and get the analysis started. So the first thing we'll do is, we'll run an analysis similar to what we did the other day. Now, we already have results loaded for this model. So if we view, the deformed model, we can also view stresses. We have results, but we don't have them evaluated against any particular criteria. When we ran the global FEA, we originally had it at none. So it was just calculating stresses and deflections. When we do the analysis, we can select one of these, and I think by default, the basic version of Maestro has the Maestro evaluation criteria, as well as, I think, HSNC, ABS-DLA, the CSR, and Bureau Veritas Naval. For our run, we can do the ABS-DLA. I'll go ahead and get this one started. If we didn't run here, the other option is to, once you have your stresses computed and you have results, you can go straight to limit state evaluation post FEA. So we have stress results and everything. This allows us to just run the evaluation. So I could run the Maestro evaluation here, and it'll ask about regenerating the patches. And if I say yes, we'll go through, regenerate the patches, and then for every single one of those evaluation patches in the model, it will evaluate it against all of the Maestro criteria. And you can see it says complete limit state evaluation. So now under results, there's an additional option here for adequacy. We'll need to take a look at what exactly the adequacy parameters are. Adequacy runs from -1 to 1. The reason I was going to rerun this from the global FEA is that you'll see under the limit state evaluation, when you go to run the criteria evaluations after the fact, it's a limited list here. There's only Maestro, ALSOP, NVR, DPC 104, and HSNC. If we are originally running from the full evaluation, the full run of Maestro, we have additional options for what can be run, including the ABS-DLA. Now, some of them are just renamed. I think the NVR is the same as the MIL 519. There are additional options when you run here, and they can probably be added. They just haven't been, because typically you know what you're going to be evaluating against, and you just run it from the very start. But the actual post-processing to run against the criteria is very quick. It's computing all the stresses and everything. That takes a little while. We'll kick this off in the background and switch over to talk about adequacy parameters a little bit while this reruns. So if we go into the Maestro help file, there is, under analyzing and post-processing, under failure mode evaluation, it talks about adequacy parameters. And basically, when we go to evaluate whether our panel is going to pass or fail, we have gamma for a factor of safety, the actual load that we're placing on the panel, and what the load limit is, the limiting value, based on whatever set of rules we're going to use. Maestro uses a strength ratio, R, which is simply the safety factor times the load divided by what the limiting load is. If that strength ratio is less than 1, our structure passes. But you can have a very high range of what R can be. So in order to sort of unify what the range is for purposes of displaying the results, Maestro uses what's called an adequacy parameter. It's created simply by this formula, 1 minus safety factor times the strength ratio over 1 plus a safety factor times the strength ratio. If our strength ratio is less than 1, which is all of our passing conditions, 1 minus something less than 1 is going to be a positive value divided by something greater than that. If we have a strength ratio that is greater than 1 because it's failing, we'll have 1 minus something greater is going to give us a negative value divided by 1 plus something greater than 1. So it's a nonlinear curve. But basically anything that is between 0 and positive 1 is going to pass, and anything with a negative value fails our criteria. Now that this is done, we can start looking at what some of our results are based on these adequacy parameters. The way the display here is broken down, we can look at any given criteria individually, say buckling, and it'll display all of our results graphically throughout the hull. And I guess with regard to exactly what those criteria are, if we look in here, like for the built-in default criteria, we have 8 different modes of panel failure and 6 different modes of beam failure that are going to be evaluated. If you want additional information on these, the textbooks are always a good source. That's essentially the theory manual for Maestro. in the help here, you can see a more detailed breakdown of exactly what is being evaluated. And then there's a similar one for the various beam theories. And there is a naming convention, at least in the built-in Maestro ones. P is panel, C is collapse, Y is yield, S is serviceability, and so forth. So panel, collapse, stiffener failure. They make sense, but if you ever need to know what exactly they stand for, and some of the other ones are a little more cryptic than this, here it has plate buckling up at the top, but you can always come back into the adequacy list and see what things are. Now, if this was the Maestro criteria, this would be a completely different menu here. It would have all of the Maestro criteria listed, although it'll have a similar structure to it. At the top, you always have all load cases. Then you'll have a subgroup of all of your plate failures and the individual ones. Then a group of the beam failures and them listed individually. And then there'll be some additional criteria that can be plotted. And then at the bottom, you'll have this also standard portion of the menu, which is minimum value for all, just display the negative results, just display the positive results. Going back to the help, they have this additional information for the Maestro and for CompSolSAP. It just refers you to these papers where you can find the actual criteria. The AVS HSNC simply refers you to there, and those documents are updated occasionally. If they make changes to the criteria, the changes will be implemented in Maestro. But rather than duplicate documentation, it's a reference to whoever came up with the criteria. That's sort of the official source for what's being evaluated. Getting back into the display, querying the results is very similar to how we deal with the stress results. We can come in and use dynamic query. We're looking at the patches right now, but in order to see any of the useful information for adequacy, we need to turn on the recovery of adequacy parameters. And you can see for that particular patch, and actually for plate buckling, we can see from our scale that the lowest value we've got is still positive. So everything in the vessel passes. We don't have to worry about failures. If we were to come in here and say, I only want to see the negative values, everything is displayed in gray because there are no negative values, and you can see there is no scale. If we switch over to check ultimate strength, again, no scale. And since we're displaying all negative, it indicates everything passes. If we see what's actually there, the minimum is positive 0.24. The other thing we can do, and this is probably the more common use, is to just say, show me the minimum value for all of the plate criteria. So here, it's going to plot the worst adequacy parameter for all of the available plate criteria. And if we come in to measure, we can see what our plate buckling, plate ultimate, and allowable stresses are. Now, some of these are at the patch level. Some of them are actually on individual elements, like allowable stress. If we hover over one element in the patch or the other, you can see the allowable stress value is changing because that one is evaluated at the element level rather than the patch. If we go down into the next group, we can say, I want to see the minimum value for all of my beam criteria. And so now all of our beams are highlighted. We do have some failures in here. You can see some negative values. Not surprisingly, these incredibly tall bulkheads with very small stiffeners appear to have an issue. If we query one of those patches, we can see the stiffener buckling is failing. It's minus 0.647. Allowable stress is fine and tripping is fine, but the stiffener buckling is failing. And here, if we tell it I only want to see negative values, makes it a little easier to see, but because those beams are so small, you might miss something. So one thing we can do is to turn off the hide elements outside of range. And now we have just a wireframe. But again, these are a little on the small side. So an additional aid to reviewing some of these structural failures is to, in the groups dialog, one of the extract options is by negative value. So whether or not we have the display of elements outside the range turned off, or whether or not we have only the negatives displayed, if we come in and say extract by negative value, it's going to grab any of the highlighted structure with a negative value on the display and put it in a new general group, and it's called negative adequacy. And if we make that our view part, now we can see only the structure in the ship that failed and by how much there. And we can also view allowable von Mises stress, quite a range going from all the way up to 1 and down to minus 0.25. So if we want to check just what failed, we can say only negative, and I'm curious what this minus 0.25 is. Where is that worst piece? I don't see much looking around the model casually here, just those two areas, which are pretty minor failures. They're very close to passing. If we zoom in a little tighter, we can see, oh, I've got some beams there. Other tall ones, I'm not seeing much. There's a few more, but nothing that was in red indicating the 0.25. If we hide outside the range, it's still difficult to see where that is. Where using that group extract can be very helpful. We say only the negative values, and we already had a negative adequacy group there, so now I create a new one with a pound sign on it. If you wanted to extract each one of these, as you extract each one, you can simply click on it again or hit F2 or right click and say rename and change the name to something descriptive of which criteria was being evaluated there. But we make that our view part. Now it's much easier to look over everything, and there is the culprit. It was a very small horizontal beam at the end of the bulkhead there. We come back into our view. Behind that other beam there. So that was the one that had the maximum failure. And as we change to a specific or any of these criteria, you'll see the labels changing at the top. So you have a quick reference to what exactly you're looking at. This, I think there's a little bug with this display in that when I change from allowable VM stress to one of these others, regardless of which of these three, it's keeping the checkbox on allowable von Mises stress. So I think that's just a graphics issue. That's a minor fix. And actually, I'll let Ming know about that, and it'll probably be fixed in the next release he was talking about. Now at the bottom here, next to the negative, there's also minimum value all, which is basically the minimum value plate and minimum value beams. And this is usually probably what you'll use when you go to evaluate. It's the quickest way to see if you've got any problems in there. And if you have something specific you're looking for, you can focus in on the individual ones to break it down. But usually an initial quick first check is you'll come into adequacy and you'll say, show me the minimum value of all the criteria and only show me the negatives. And then you can see exactly what portions of the structure have an issue for any given reason, regardless of what's causing the problem. Find out which areas have a problem. The other thing you can do in here is to check all of the load cases at the same time. We only have 4 defined in here, so we could cycle through these fairly quickly. We change load cases, and final mass and additional mass were essentially the same thing. So we have very similar displays here. If we switch over to sagging, you can see our scale changed there. We still have issues primarily with beams, but now our girders are lighting up a bit. They were not a problem for our still water. And if we go to hogging, we can see we've got some structure on the bottom that's starting to fail. And if we hide outside of range, we can see if there's any additional structure in there. And there is some on the interior on that longitudinal floor that we couldn't see because it's completely enclosed. But when we hide elements outside the range, it makes it a little easier to find these things.